So, welcome. Again, Devoxx France 2019. I've been here last year. I don't know if you saw my talk. My French is not very good, but je suis très français. So this year, if you've seen my talk last year about what's called Twitter's Quest for Holy Graal Runtime, where I talked a lot about how we started using Graal at Twitter and running our microservices on Graal. This is basically the second part of that talk. And this time, you'll see pretty much the same graphs and everything. We will look at our tweet service, the performance of the tweet service, and also another service called Social Graph. But this time, we're using AUTOTUNE to improve performance. So that's what this talk's about. If you, and I've already noticed yesterday, because the hashtag DevoxFrance was actually trending on Twitter, so you guys are all using Twitter, thank you very much. Who in this room has a Twitter account? Half. Okay, so you guys need to create one right now, because I want you to tweet about the conference, you know? Tweet about the conference, tweet about the talks you like, tweet about, I don't know, the booths, the stands, whatever, the free goodies you get, anything. If you tweet about my talk, at that hashtag Twitter VM team, because Twitter has a VM team, and it used to be last year we were only 4 people, but this year we're already 8. So we are growing in size, we do different things. We have still like 3 core GC engineers, and the GC engineers take care of all the GC issues that we have, and everyone in the world has GC issues, and so do we. Then we have me, the compiler engineer. Then we have a colleague of mine. He's also working on the compiler. We just hired a 3rd person who will work on the compiler. So we're investing more and more into the compiler work and Graal. And then a bunch of other people doing different things, one of which was doing AUTOTUNE. That's the tool we're going to talk about today, the machine learning tool. So tweet about this at the hashtag, and everyone knows that I was here. This is me, still me. I was working, and I am working for many, many years on the JVM. That's pretty much what I do all my life. And most of these 14, 15 years almost by now, I was working on JIT compilers, okay? So I'm going to ask you a bunch of questions so that we're all on the same page. Do people know what a JIT compiler is? Yeah, that's pretty good. So in a nutshell, a JIT compiler just takes Java bytecode of whatever language you compile down to, Java, Scala, Kotlin, you name it, into Java bytecode, and a JIT compiler. People know what a JVM is, right? JVM, yes. Hotspot, we know Hotspot. We know the JVM of OpenJDK. The JIT compiler in the JVM takes the Java bytecode and compiles it on the fly while you are running your application into native code, so that your application runs faster. You know, unlike AOT, ahead of time compilation, like GCC, for C++, you do it upfront, we do it just in time. So I was working on this. I was working at Sun Microsystems at Oracle in the Hotspot compiler team, so I was mostly working on C2. Do people know what C2 is? All right. So Hotspot has 2 JIT compilers. One is called C1, or client compiler, and the other one is called C2, or server compiler. You might have heard the client and server names before with the dash client and dash server we used many years ago. So C1 is a high throughput compiler, so it compiles code quickly. It doesn't optimize as much, but we want to get away from interpreting code to run on native code as quickly as we can. And then we run on that code, we collect some profiling information, and then later on we recompile with C2, the top tier compiler. That one produces peak performance code. It does a lot more optimizations, does a lot more inlining, escape analysis, loop unrolling, all these things. Okay, so I was working on C2. And that compiler is pretty old. You know, I bitched about it last year, I'm sure I was. These are the 3 things, the biggest project I worked on during my time Sun Oracle. JSR 292 is Invoke Dynamic, support for dynamic languages. If you're using Lambda in Java or something like this, you're using Invoke Dynamic under the hood. I was writing a lot of that stuff. We had 2 different implementations. One that was a lot of handwritten assembly code in the JVM. That was very hard to maintain, had one big performance problem. And so we redesigned the whole thing and moved a lot of the logic that was in the JVM itself into Java, into a package called Java Lang Invoke. And so now most of it is written in Java, and I wrote a lot of that Java code as well. So if it doesn't work, you could technically blame me. But a lot of people touched the code after me, and my code was perfectly fine, and they broke it. So chap 243, Java level JVM compiler phase, we introduced that in JDK 9. And basically what we did is we took Graal. Okay, who knows what Graal is? Not Graal VM. Yeah, see? Difference. So let me talk about this real quick, because it's important to understand the difference. So Graal VM is a product. I don't know what to call it. It's a marketing term that Oracle Labs came up with. And Graal VM is like a marketing term that spans, an umbrella term that spans over 3 different technologies. Graal, the JIT compiler, right? People know what a JIT compiler is? I explained it, yes, all hands up. The Graal, the JIT compiler, Truffle, which is the framework to implement language runtimes, and Substrate VM, which you might know as native VM. That's what most people are excited about. I'm not talking about Substrate VM or Truffle. I'm only talking about Graal, the JIT compiler. So when I say Graal, I only mean the JIT compiler. It's very confusing, and I get into arguments on this every now and then on Twitter when someone says, oh, I'm running my stuff on Graal VM. What do you even mean? It doesn't mean anything. What is it? Are you still running on hotspot with Graal, the JIT compiler, or are you using native image? It's very confusing. So we took the interface that Graal is using, or was using, well, it still is. We took the interface that Graal was using and extracted it out of the Graal project and made it it's not an official API, but we made it a somewhat stable API. And that's that, chap 243. So there's now an interface in Hotspot where you can plug in an external JIT compiler. And then chap 295, we did 243 because of 295. Ahead of time compilation, it's not the same as native image. This is different. It's basically a command line utility, and you pass in class files or jar files, and then it sends off, it uses Graal to do compilation, and then it spits out a shared library at the other end. And Hotspot can pick up that shared library. It basically, it can, we've seen it sometimes, improve startup of your applications. If your application is very big and runs a lot of different code when it starts up, that might help. Okay, and now work for Twitter. Greatest company on the planet, we all agree? Very good. This is Twitter. That's what it looks like. At least it did, what, 3 years ago. So we have hundreds of microservices, and we have thousands of instances of these microservices. And we run on heterogeneous hardware. So we own our own data centers, so we own our own hardware. We know what hardware we have, but still our hardware is heterogeneous, right? It's newer versions of the same chip, or blah, 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 where Intel comes out with a new thing, so we bring in a bunch of new machines. You probably run in the cloud somewhere. You don't even know what hardware you're running on. So the problem is, with performance optimization, hand tuning in general doesn't scale, right? So you can only handle a few parameters because you kind of have to build up a mental model to understand what's going on. It's very time-consuming, labor-intense, error-prone. The way it usually works is you at your company or one of your colleagues at some point will get annoyed by the performance and we'll sit down and hand tune a little bit, right? That happens every 3, 4, 5 years when you get annoyed enough that you do it. And then you forget about it. Then that person leaves, goes to another company, no one knows what the hell was he doing. So this is the main issue. And then the last point is very important because we are all living in an, whatever it's called, agile world, and you're redeploying multiple times a day. We redeploy some of our services multiple times a week. We don't do multiple times a day, but we do weekly things. So if you tune today, you tune for today's code, but tomorrow it might be different, right? Maybe not a lot, but in a month it will be different because code is constantly changing. So many services operate below optimality. And this is certainly true for Twitter services. So you're throwing money out of the window. You really are, because you're using way more machines than you need to. So this is kind of a very theoretical part. I want to just briefly touch on, and I know nothing about this, briefly touch on what performance tuning is. So basically you have a function, and you want to optimize that. Well, it's a function defined over domain X, right? And then what you want to do is you will find a configuration that maximizes F, whatever F is for you. Throughput, reduce CPU, less memory, I don't know what it is. Reduce latency, something like that. And the thing that's very important, it's always subject to a constraint. So the number one constraint is it still has to work. And we will see that later. You can tune too far, right? You crank up one of the knobs and it goes too far, it doesn't boot up anymore or whatever. Or latencies are too high, it could happen. And it actually does. So this is what performance tuning in general is. You pick a parameter to test, then you put an instance, you start up an instance on the system, you measure whatever you want to measure, then you take the measurement, and a performance engineer has to look at this number and has to decide, was this better or not, right? That's very expensive, like time-consuming, and having a person doing this. We could possibly take a monkey, I don't think we could, but what we want is a black box thing, and we don't even have to know what it does or how it does it, right? We just need an answer, was it better or not, and what value of the parameter to try next. That's all we need. So what we use for this black box thing is something called Bayesian optimization. It's a method to learn potentially noisy objective functions. Important, it's doing it iteratively and efficiently. We want to do multiple runs of whatever service we are running, and then we want to have a result as quickly as we can. Because if one of these runs would take a month, that would be way too long, because we're tuning code that is a month old, or even worse, the code is changing every day, and then every day we're running something different. So it would be very, very difficult to find an optimizer. But it finds near optimum in a few iterations. That's important. Works well with nonlinear multimodal high-dimensional functions. That's the important one, because the JVM has hundreds of parameters you could tune. Right? Someone asked me not too long ago, I gave this presentation, someone asked me, well, could I tune my database? Well, hell yeah, you can. It doesn't matter what it is, right? I'm just talking about the JVM, but it could be anything. So if you're interested in how all this Bayesian optimization stuff works, then listen please to my colleague. He can explain this much better than I do. He gave 2 presentations on this topic, one at Devoxx a while ago. He has a very soothing voice, much better than mine, so listen to him. And if you look at these slides with the graphs, the top left one with the dots in it, basically what I did was I stole his slides, and I'm trying to explain it to you real quick. The reason why I'm doing this, and again, I'm not an expert. If you know what Bayesian optimization is, please be quiet. I'm just doing this so you can understand better later when we look at graphs and the performance number results, you can kind of understand what it did. So I'm briefly going through this. So we have a parameter that goes from -6 to 6, and then performance is the y-axis, and higher is better. And we did 3 evaluation runs, and these are the actual results, right? The actual performance curve looks like that. The points obviously are on the curve because it's real results. And then what Bayesian optimization does, it assumes a curve with some certainty. That's the blue area above and below the line. And then what it does, the Bayesian optimization, you take your best result. Oh, sorry, yeah, that's overlaid with the actual curve. You put in a line with your best result, and the blue area above the red line is the expected improvement graph at the bottom. The more blue you have, the higher it is at the bottom. And that's the point which you try next. So you pick the highest one, that's the one on the left, that's the second one. You try that, you run the evaluation, you get another data point, right? And then you explore that space, and now we take the one on the very left, we try that one, yeah, that was pretty good. then one to the right, okay? And we've explored that space here. So we found the optima for that area. So then we go to the right, we try this one, that sucked. Then we try the one to the right. Oh no, the one on the very left, yes, that was also not good. Then the one on the right over there, oh yeah, that's pretty good. And then we try this, that one, until we found the global optima. That's all Bayesian optimization does. It's pretty much what you would do as a human as well. It's just stupid to do it as a human, right? And this machine can do it much faster than we can. That's all it does. So we use Bayesian optimization, but it's non-parametric, robust, extensible, well-tested on many systems of real-world high-impact problems. So basically what we're trying to say is the goal, and we're not there yet. We're unfortunately far away from this goal, but what we want is to have this Bayesian optimization service on all the time in production. It should constantly tune itself, right? I don't know how long runs would be or how long it would take. We would have to figure that out. But now it's basically a one-off experiment type of thing when I do it as a human, but it should actually be on all the time. Good, let's look at experiments. So what is AUTOTUNE? It's Bayesian optimization as a service. As I said, I called it a BOAS, so make that trending, make a hashtag of it, make it trending. We're using something called WetLab. It's a company that we acquired a couple years ago, and basically what they did, they took this this Bayesian optimization framework called Spearmint, which is still open source, and just enhanced it, right? It's a little better, as far as I know, than Spearmint is, but if we're ever going to open source the AUTOTUNE part, someone could adapt it so that it still works with Spearmint, and then you could use that as well. AUTOTUNE itself is really just a driver for the experiments. It's basically, it starts and stops instances, your evaluation runs, and talks to the Bayesian optimization service. Okay, I have these and these parameters, please tell me the values what to try next. That's what AUTOTUNE is. It's really a tool, more or less. Okay, what is Graal? What is Graal? Everyone knows, I explained it earlier, very good. Can you explain it again? No, sorry. Java Virtual Machine just-in-time compiler. It's actively developed by Oracle Labs. You might notice there's an official OpenJDK project for it, actually. It's not much used, let's put it this way, because most of the work is being done on GitHub these days. So you can get Graal there, file a PR, blah, blah, blah. It uses JVM CI, and Graal is written in Java. That's not important today, but if you want to try Graal, you should, if you have time, probably watch this talk of mine. I gave it here last year in French. No, I was not. How to use the new JVM JIT compiler in real life, which basically explains to you a little bit what to look out for if you run benchmarks, right? But that's what you do, right? You think, okay, when you go to your manager and you say, I would like to, can we use Graal in production? He probably would like to know why. And then you could say, well, you look at this runs faster, and blah, blah. So this explains it a little bit. Okay, so which parameters did I tune? I picked 3 parameters that are inlining related. Do people know what inlining is, optimization? Yes, I think most people should know. It's basically taking methods and copying the code into the caller so that we can compile it better and run faster. It does that in the JVM, right? It's the reverse of refactoring, basically. So there's one called trivial inlining size, and the number 10 means nodes in the compiler graph. So when you compile something, a compiler, what it does, it parses in some source language. It might be source code, it might be Java bytecode, and it builds up graphs, right? If the method has less than 10 nodes in the compiler graph, we inline it all the time. We don't look at any other thing, we don't look at profiling information, we just inline it because we know it's trivial. Then maximum inlining size is basically the other end of the spectrum. If it's more than 300 nodes, we don't inline it. And small compiled low-level graph size, it's pretty much the same as the second one. It's just at a different level, and in the compilation. So most compilers have two different representations of a compilation graph. There's a high-level and a low-level representation. And the high is just high and the low is low. That's how I explain things. Low means low. No. Higher is closer to the source language, and low level is usually very close to the actual machine instructions. That's how it works. Okay, these I'm tuning. I'm tuning these because inlining is the mother of all optimizations. If you get inlining right, it enables a lot of other optimizations, especially escape analysis. If you inline more, escape analysis can work better. Escape analysis is, I'm not going to explain it, but it can get rid of object allocations, right? That's what it does. Good. Okay, previous work. You've seen this talk last year, maybe, and I was giving this example of how much do we reduce GC cycles and CPU utilization by running with Graal. So this is GC cycles, and we reduce by 4.2% by running with Graal instead of C2 for the tweet service here, which is already very nice. And then I did what I told you earlier to not do. I hand-tuned it, right? I was sitting down in the afternoon, Friday afternoon for 3 hours and tuned it, and I got it down another 1.5% of GC cycles. That was pretty cool. And this is CPU, and just by using Graal, we already used 13% less CPU, which is great. And I could squeeze out another 2 by hand-tuning it. I was very proud of that. Thought I deserve a beer, which I probably had. And I didn't get the money that thing saved, but that's another story. So what ranges, what I did was I gave the parameters I wanted to tune actual ranges from where to where AUTOTUNE should look for, like the Bayesian optimization part. I did this, you don't have to do it. And if I would do new experiments, I would probably not do it again, because you can say 1 to 1,000, or 1 to 1 million even, if you wanted to, because it would figure it out itself, right? It would assume ridiculous numbers and then the thing wouldn't work, but it would eventually find the global optimum for F. I did it here because I know the service really well, and I wanted it to finish in a certain amount of time for slight reasons. I wanted it to fit on 24 hours, basically. Okay, so we're tuning these in these ranges. The test setup, I'm always using the same test setup, and if you do performance measurements, and if you know that the expected improvements are small, you need dedicated machines. You cannot do something like this on shared machines. Because the crosstalking of other services, you have no clue what else is running on your machine. It might completely, lock up your network connection, I don't know what. So I have dedicated machines. All instances receive the exact same requests. It's very important. It's not only the same number of requests, it's the exact same request. And the reason this is important is, for the tweet service, a tweet could be 1 character long or 280. So the memory allocation pattern would be very different. So all of the instances, they process the same tweet request at the same time. We run with that JVMCI version, that Graal version, not very important. Default tiered C1 Graal setup. So basically what we do is we take hotspot and just replace C2 with Graal. We still do tier compilation. I'm not going to explain it now what it is, but most people know, I hope. Good. Experiment 1, tweet service. Still the same service as it was last year. It's a Finagle thrift service. Finagle is one of these frameworks written in 92% Scala. That's important here. That's the important thing on that slide. That is mostly written in Scala. It's something we open sourced where most of our services are built on top of Finagle. It's an extensible RPC system for the JVM used to construct high concurrency service. I have no idea what it is. I really don't. And I don't have to know. So, objective. This is basically what we are trying to improve, maximize. And as you remember, So we are running in Aurora on Mesos. So this is Aurora, and we are trying to improve something called user CPU time. So we're trying to reduce user CPU time, and as if you remember, Bayesian optimization always looks for a maxima. So what we do here is just 1 divided by, right? We're just trying to improve that one. And then we have a constraint, and I only picked one constraint because it was easier to do for me. If this would be, as I said, always on in production, it would have way more constraints, right? You would have to go to the service owners, ask them, what constraints do you usually use to make sure so that you know if your service still runs fine? You would have to use all of these constraints. But the constraint I used was, you can see it here, are we throttled in Aurora? Or I think this is Mesos actually, are we throttled in Mesos? If you're doing something wrong and you're using too much CPU, then you get throttled, and you know, okay, this is not working well. Okay, so this is the result of the first experiment. It's 24 hours of tweets, and you can see the curve, and we have in blue the experiment, and in orange the control. And then you see these slices, they are 30-minute long slices. These are my evaluation runs. So one evaluation run was running 30 minutes, and then it was talking to the Bayesian optimization part again to get a new value for the parameters, and then restarting another evaluation. I only did 30-minute evaluation runs. They're pretty short, but I know the tweet service really well, so I know that in half an hour, everything was started up, everything's being compiled, it gets to a steady state, and period. If we would do this, as I said, always on in production, these would have to be longer. For the tweet service, it could be 30 minutes, but we would have to pick a length, and I'm not sure what the right length would be. We would have to find out, I guess. Maybe it's a day, maybe it's 12 hours, 6 hours, I don't know. Because we don't know every service, right? We would have to find something that would work for most services well, and then we don't have to change the parameters, the configuration we found out every day, right? We don't have to tune every day. If we tune once a month, it's probably still good enough. We're much better than today. Once a month versus never, right? So, okay, user CPU time. That's the result. You see if the blue line, the blue curve, is below the orange one, that's an improvement. Then we used less CPU. And that happens a bunch of times. And this is what AUTOTUNE gives you. It gives you a table of your results. And it's sorted by objective. And the objective is 1.0838. That means that we reduced user CPU time by 8.4%, which is amazing, right? Hand tuning got me 2, and I was proud of my 2. But this is much better. 8 is ridiculously good. Then the second one is 8.1, and then we have a 6.4 and 6.46, roughly, right? So even if we would say, okay, maybe the first 2 ones are outliers, we would roughly get a 6% improvement. That's amazing. Then you see the values for the parameters that it found. And this is the top of the table. The bottom of the table looks like this. And as you can see, 3 evaluation runs actually violated the constraint. So we tuned it too far. It did not work. So as I said earlier, it's very important to do this, but it actually happens. Then what we can do is we can look at the charts for the parameters. And this is the trivial inlining size. Keep in mind that we're exploring, because we're doing 3 parameters here, we're exploring a 3-dimensional space. Right? If you use more parameters as an n-dimensional space, it's impossible to visualize on a 2D slide. So every data point in that chart and the following charts depends on 2 other values that are not the same. Right? So take this a little bit with a grain of salt, but it gives you a rough idea, a trend. And you can, if you squint a little, you can actually see a trend. You can see a trend going up if you go higher. So default for this one was 10. That's where we started, actually, and we ended up at, what's that, 21 or something like that. that would be a much better number for this particular service. This is the maximum inlining size. It's kind of flat, right? We have the two outliers at the very right. They might be outliers, but maybe not, because again, they depend on two other values. So maybe that's just a very good configuration. And this one, you don't even have to squint to see what's going on, right? The default value for this one was 300. And then we tune up to, what's that, 600, something like that. So this one certainly, especially for this service, should be much, much higher to get better performance. What I did then was, to verify the results, I did a verification experiment. I basically took the first line of the result table, put the configuration in our, the result in our configuration file, and ran the tweet service for 24 hours. And that's it. So we are doing blue is C2, orange is Graal, and the red one is Graal with the AUTOTUNE parameters. They all are the same because it's requests per second, and as I said earlier, it should be the same. This is PS scavenge cycles. The tweet service is using parallel GC. So we're looking at scavenge cycles here. And we could reduce in that particular run by 3.4. We've seen that a similar graph earlier. So 3.4, then AUTOTUNE looks like that. It's another 3.5, which is amazing because that's a total of 7%. We can Graal, by just using Graal then, instead of C2, we reduce it by 3.4. But the important part here is, if we tune it, we can reduce it by the same amount again, which is great. So that's the money throwing out the window part, right? And we look, oh yeah, it's basically the same number in a different graph. Maybe it's easy to understand for people. It's allocated bytes per tweet. It's pretty flat. It fluctuates a little bit, depends on a little bit on the tweet length, obviously. But it's the same number, right? We reduce by 3.5, 3.4, 7 across the board. When you see it's over the 24 hours, it's very flat. User CPU time, in this particular run, it was 12% that we reduced. And then this is AUTOTUNE, and it's another 6.2, up to a total of 18.2%. It's ridiculous, right? I mean, again, 12% is already amazing. And last year we were all excited about this, at least I was, I'm not sure if you were. But then we tune it, and we get another 50% on top. It's great. So we can, for the tweet service, reduce the instance size for the tweet service by 18%. It's a lot of money that we don't have to spend. Then I looked at P99 latencies for the tweet service. I look only at 2 nines, because if you go more than 2 nines, 3 nines or 4 nines, the only thing you're looking at is your longest GC, right? So if you look at 2 nines, you actually get a real representation of the world, and it's still 99% of the tweets. You can certainly see that we reduce CPU with Graal, and we also reduce latency for that. This is AUTOTUNE. You can see that it's better than Graal, the default one, but it's a little bit hard to see how much that is. So basically what I did is I integrated over the 24 hours, and that's that graph. That's what it looks like. And then this is the result. So by just using Graal instead of C2, we reduce P99 latencies by 20%, which is great. Everyone would be happy about that. But then we tune it, and we get another 8. And then we have 28% lower P99 latencies. That means if you scroll on Twitter, you get your tweet 28% faster. You could read 28% more tweets if you're really fast. I encourage you to do that, by the way. Makes my stock price go up. Experiment 2, social graph. So I did the same thing that you just saw for the tweet service with another service called social graph. And it's a abstraction for managing many-to-many relationships at Twitter. It's basically who you follow, who follows you, right? It's kind of an important service. It's again finagle thrift service, pretty much the same what we've seen before. It runs on top of, how does it go? We use Netty and then finagle and then the logic of the service. And I just wanted you to show a different one because the results are different. Okay, objective, pretty much the same. We try to reduce user CPU time. Constraint, exactly the same. If we get throttled, we kick it out. That's the experiment. It's a different curve, obviously, because it's a different day. But again, 30 minutes evaluation runs. This is the result. No, it's not, sorry. This graph uses CPU time. We've seen it before. This is the graph. So the top one is 7.6. That's pretty good. It's like before we had 8 point something. I can't remember. Then we have another 7.6, a 7.2, a 6.8, a 6.5. So let's say, well, maybe we get 6% improvement. That's roughly what we saw with the tweet service as well, at least in AUTOTUNE. Then the bottom of the table looks like that. We had one that violated the constraint. Don't pay attention to the 3 ones that are running. It's probably a bug. These are the graphs. Trivial inlining size. Still a slight trend, but not as obvious as with the tweet service. This one, maybe there's a trend, but I don't really see one. Like the one that's the best, where is it like 400? It's pretty much like in the middle of our range. And then this one is important. It's not as obvious as the one for the tweet service, if you remember, but you see the result is like 649 or something, right? And the range was from 200 to 650. So I think I shouldn't have done the range here, because I'm not sure if we would get higher than that, it might be better for that service, actually. Good. Did an experiment, a verification experiment. Same thing, 24 hours of requests. And the social graph service uses CMS. So we are looking at par news cycles here. And we can only reduce the GC cycles by 1.6% when we use Graal. So it's less than with the tweet service, but it's just the way the code is written. If we cannot get rid of object allocations because that's just the way the code is, then that's it. We can't do more than that. But interestingly, if we tune it, we can reduce by 3.5, up to 5%, which means we get way more out of it by tuning it than by just using it. So it's all nice and cool, but pretty much the whole world, I think, is not really tuning the compiler in Hotspot or the JVM. We are throwing away a lot of money. And we also, I'd like to say this, we own our own data centers, right? So we certainly, if we don't have to use as many machines, we save a lot of money by not buying these machines and stuff. But we also don't spend money for electricity. We don't have to do the cooling and blah, 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 right? So what we're trying to do is we try to save the world. That's really it. I don't care about anything else. So user CPU time for a social graph, that's about 5.5, which is less than the tweet service. Tweet service was 12, right? 5.5. I think a lot of that is because we cannot remove as much object allocations. Because if we can remove object allocations, the code gets tighter, it runs faster. We also don't have to do the GC cycles, which uses a lot of GC, a lot of CPU. So this is why this is not as much. This is AUTOTUNE, and the interesting one here as well is it's more than we can tune than we get by default. The interesting thing I want to point out here, because someone might see it, and I cannot really explain it because I didn't have time yet to look into it, but if you look at the difference between the blue and the orange graph curve, it's pretty much the same, doesn't depend on the load, but the red one does. The red one over here, when the load is lower, is less improvement than when the load is high. And the 7.4 is where the load is high, because I want to look good on stage. I'm not, Good. All right. Any questions? There should be, many people should have the same question, and the question should be this. Right? Was that your question? I'm so good. And the answer is, of course I did. because I could not come up here and talk about how great Graal is and then not try it with C2. So I did an experiment with the tweet service, and these are the parameters I picked for C2. The max inline level does not exist in Graal. So I tried to pick 3 that are very similar to the ones I tuned for Graal. But the first one does not exist. The max inline level basically tells C2 how deep it should do inlining. So how many call levels deep it goes. And it only goes to 9. It's not very deep. And it's important these days, I think, when everyone's using a trillion of frameworks and that framework's calling this framework, calling, you never actually inline the shit that you want to inline because it's too deep. So we picked 9 years ago. It was even way before I joined Sun, which I think is way too low for today's code. It might have been fine 15 years ago, but it's not today. Then max inline size has the same name as the one before. The difference here is the 35 is bytecode size. It's like before it was nodes in the graph, but here's actually bytecode size in your class file. This one, if you ever had a, only 4 minutes left, all right, hurrying up here a little bit. This one, no, I skipped this then. I'll tell you later maybe. Inline small code, 2000. It's a very interesting one. I never fully understood why. It's 2,000 bytes of native code. So if C1 already compiled the method and it's bigger than 2,000 bytes in native code, C2 doesn't inline it. It's weird. But it basically, I think the rationale behind it is if it's 2,000 bytes, it's very big. So let's not inline it. Okay, what ranges? I gave it ranges again for the same reason, because I wanted the thing to finish earlier. For the max inline level, I actually went to from 5, a lower value than the default value, because I wanted to see if I actually would change anything, to 20. Good. Same thing, different day, 30-minute evaluation runs. As a result, certainly differences. As we can see, there's a really bad or good one over there. And that's the result. So there is, the top one is 5.1. Then we have a 3.8, a 3.5, a 3.3. I truly believe that the 5 is probably an outlier. So let's say, let's be nice to C2 and let's say we see a 4% improvement, which is nice. It's really good. So if you could improve your performance by 4%, that would be cool. The thing here is, well, no, let me say first, AUTOTUNE certainly does its job, right? AUTOTUNE does exactly what it should be doing. It tunes whatever you tells it to tune. It tunes really well for Graal. It tunes pretty good for C2. It might tune your database very good as well. I don't know. So certainly the technology works. The thing here is 4% is nice. Do I have another table here or no? Yes, that's the bottom of the table, right? So we didn't have a constraint violated or anything, but I think that's the last slide for, oh no, yeah, right, I have the charts. So certainly, let me say this after the chart slides. This one is obvious, right? You don't even have to squint or anything, like the trend is so obvious. And you can see 5 is certainly a bad idea. The default is 9, it should be 16, 17, 18, something like that. That's what it should be. And I'm arguing that it should be that for the whole code in the world. This one is flat. That kind of surprised me a little bit because 35 is not a lot. So I thought that might actually change something, but it did not. And this one is completely flat as well. That didn't surprise me too much. It's just a weird thing, and it also has some race conditions in the compilation queues that I could explain it to you if I had more time. But so that was interesting. So that was the last one, right? I wanted to say about C2, I forgot. No, I forgot. Let me talk about the summary, because I had 30 seconds left. So my summary, and you might have seen it before, it's just that. That's how you turn on Graal in OpenJDK if you're on JDK 10 or later, right? So if you run on the latest LTS 11, I tweeted this a while ago. You can find this on Twitter if you can take a picture or something. I do all these presentations for one reason. I want you to try Graal. And there are some reasons for this. The number one reason is because I'm a very nice person. I want you to save money too, right? I want you to help me to save the world. Let's get down the cooling costs. The real reason is we want Graal to become a better, more mature compiler. And we found, if you've seen my other talk, the Twitter's Quest for Graal Runtime, when we started running services on Graal, we found a few bugs. We fixed all of them. I think there were 4 bugs. I explained all of them in the talk if you're interested. We fixed all of them, and since then, and that's like 2 years ago, I think, we didn't find a new bug. Like nothing. We never had an issue in production. And we are running the tweet service. You've seen the social graph service, another big service, the user service, and then 20 other not as big services, but important services for Twitter. For roughly 2 years now, 100% on Graal in production. Like everything you see and read on Twitter is basically, it runs through code that was compiled by Graal. And we never had a problem. Did you lose a tweet? I did not. So, but the problem is if we want to improve the compiler, we have to find the edge cases, right? So Oracle Labs is running SpecJBB for the millionth time. They're not going to find a new bug. Our code is very similar at the bottom of the stack. It doesn't change too much, right? So we haven't found a new bug. What we want is your shitty production code that finds the bugs. So if you can, then please try it. I'm sure you all run on JDK 11 in production. So just on Monday, you go into work and turn it on and then check out for the week. But you probably have a staging environment or something like this. You're not pushing new code directly to production. I hope you're not. But you have some staging environment somewhere where you could try it, I think, or maybe a nightly testing run or whatever you have. Or a pet project that you work on at home. Try with that one. It doesn't really matter how big it is. It's just usually the code shapes that matter. And that's just the way code is written. So different languages would also be very interesting. We do a lot of Scala. Kotlin would be interesting. Clojure would be very interesting. Because the compilers, the source compilers, produce different code shapes. That's what we want to do. Yeah, and since I'm over time, I'm stopping here now. I could go on and on and on with this monologue. Why it's important, why I think it's important to get Graal become the default in OpenJDK. The last thing I say about this is you've seen the potential, right? 5% for C2 is great, but we already had 18 with Graal. I mean, this is a different world. And the potential, my colleague Flavio, the things he's working on Scala-specific compiler optimizations for Graal. If I tell you right now the percentage improvements that he gets, it's mind-boggling. So the potential with Graal is just so much bigger that I would like this compiler to become more and more used by people. And also to, so that you save money. And then next year when you come to my presentation, you can say, we saved so much money, I buy you a beer now. That's the only thing I have. All right, cool. Thank you very much.